Good morning to everyone. So myself, Dr. P. PADMAJA. Today I'm going to explain about the introduction part related to the linear IC applications. As per the syllabus, the first unit is integrated circuit. So in this unit, we are going to study about the integrated circuit basic information, that is characteristics related to the op-amps and classification of ICs and some parameters, that is measuring parameters related to the IC 741. The contents in the first unit is mainly classification of ICs, IC 741 pin diagram, op-amp characteristics and block diagram of op-amp, ideal and practical characteristics of op-amp, and we will observe some modes of operations related to the op-amp, that is inverting mode and non-inverting mode. Before going to the contents, we will define what is an op-amp. Op-amp is as we are saying, it is an op-amp, operational amplifier. So op-amp is a direct coupled high gain amplifier where it consists of one or more stages of differential amplifier followed by a level translator and an output stage. These are mainly used in our day-to-day life, that is in communication system, controls, signals, and instrumentation, computer, and everywhere in the nowadays we are using these ICs. Mainly, we will see the classification of ICs. So mainly these ICs are classified into two types. One is digital ICs and linear ICs. Digital ICs means the discrete digital circuits designed or fabricated in the form of ICs. Those are known as digital ICs. Linear ICs are also called as analog ICs. The discrete transistor circuits fabricated in the form of ICs, and those ICs are known as linear ICs. Again, these integrated circuits are classified as mainly two types, we will see, that is monolithic circuits and hybrid circuits. Mono means single, lithic means stone. On a single stone, entire circuit is fabricated. So it is named as monolithic circuit. In a hybrid circuit, it is a combination of monolithic with some external components like capacitors and transformers. Because higher values of capacitors are difficult to fabricate in the form of ICs. And transformers, mainly we'll observe that transformers are mainly they are leaky in structure. So in order to difficult to fabricate those transformers, higher value of inductors and capacitors, we need to connect them in external. So that is known as a hybrid circuit. So again, these monolithic circuits, as we said, these are mainly fabricated for the analog signals, the discrete transistor circuits designed by using, that is designed for linear applications, those are called as linear applications fabricated in the form of ICs, right? So why we are going for ICs? We have different types of discrete transistor circuits. As ICs are small in size and they are less in cost and less in weight and consumes less power, and they are highly reliable. So they can compatible with all other devices, and the propagation delay, it's called as a speed of operation, is also more in ICs. Again, these ICs are classified based on the number of transistor circuits used. That means a device which consists, a circuit which consists of hundreds of transistors, then it is called as a small scale ICs. And a circuit which consists of 100 to 1000 transistors and fabricated the circuit in the form of ICs, those ICs are known as medium scale ICs. Similarly, large scale ICs, very large scale ICs, ultra large scale ICs, and giant model. So these are the different types of ICs, classification of ICs based on the number of transistor used, circuits, and those circuits fabricated in the form of ICs. So that is about the classification of ICs based on the transistors. Again, based on the packages, they are mainly classified into metal can, dip package, and flat package. Metal can package, it is also called as transistor package. As we already seen in our lab, the transistor, there is a metal cap in which tip is enclosed and the leads are provided for connection. It is known as a metal can package. Dip package, it is also, it is nothing but dual in line package. Everywhere we are observing this dip package, dual in line package. And here there is a ceramic block on which chip is mounted and the leads are provided for connection on two sides of a ceramic block. That is known as a tip package. And flat package, here the leads are provided flatly. It is in olden days they used this. Nowadays we are not using this type of packages. So see the diagram. So this is the dual in line package. So observe that here the two on the two sides pins are provided for connection, right? So this is a small IC and this is consists of approximately 16 pin ICs. So based on that they are classified. This is the metal can pack. As I already told, it is also called as a flat package. Observe this, there is a metal cap in which chip is enclosed and the leads are provided for connection. So this is the pin diagram for an example for a op-amp, operational amplifier. So, and this one is a flat pack. As I already said that is there is a ceramic block on which chip is mounted and the leads are provided flatly for the connection. So we'll see these diagrams. So after that, these are some of the examples. So this one is metal can and these are the dip package and this one is a flat package. So this is the classification of ICs. Not only this, based on the temperature, we are using these ICs in our commercial purpose, that is in the laboratory environment, and we are using some ICs in industries where in some industries there's more cold and there's more and less heated. And similarly, in military environment where the temperature is more. So based on the temperature, these ICs are also classified. Yeah. Right. Now this is the pin diagram. So what is it? We have already seen the definition of an op-amp. Op-amp is an operational amplifier. Operational amplifier which is a high gain. It's a direct coupled high gain amplifier. Right. So why it is called so? We are saying that op-amp. What is an op-amp? Operational amplifier. By the name it is given because it is mathematical. It is used for the mathematical applications like adder, subtractor, integrator, differentiator, log, antilog, many other mathematical cells. So it is the name given as a, it is used for the mathematical application. So it is named as an operational amplifier and we are shortcut, we are calling this as a op-amp. Now, so these op-amps everywhere we must consider the power consumption. So power supply, the range of operating. Here op-amp is operating between plus or minus 5 volts to plus or minus 22 volts. So because op-amp is mainly consists, if you observe this diagram, op-amp it is an 8-pin IC 741 is an 8-pin IC. Right? We will further discuss the pin diagram of op-amp. Right? And these op-amps are manufactured by the different companies. So these are failed company, National Semiconductor Materials and Motorola, Texas Instruments, Signetic Company. These are the different companies. They are manufacturing these op-amp. So whenever you are buying any component, we will observe some numbers. Along with the numbers, some letters. So for example, mu A741. 741 is the IC number that is given for that component. We already know transistor PC107, right? B means silicon, and C is a it is a semiconductor. B is a silicon material, and it is used. It is a transistor type of component is transistor. Here also in the same way, we are using mu A. Mu A is the company name, that is Fairchild company. They are manufacturing this op-amps. And similarly, LM, SN, right? MC, Motorola. We are observing many ICs related to different companies. The next, we will see the block diagram. As we have seen, op-amp, it is in our subject, we are mainly studying about the IC number 741, which is an operational amplifier. It is an 8-pin IC. It consists of inverting input, non-inverting input, plus VCC, minus VCC, output. And 8-pin is no connection. And we have two more pins, that is pin number 1 and 5. Those two pins are known as offset pins. So further we are going to discuss about these pins 1 and 5, which is used for nulling the output without any input. So we are using for the compensation purposes. So op-amp is mainly symbolically represented as like this. That is, it consists of two inputs, two power supplies and output. As we already seen, inverting is pin number 2 and non-inverting is pin number 3. Positive supply voltage is pin number 7 and negative supply voltage is minus, that is minus 12 volts, which is related to pin number 4, and output is pin number 6 that we already seen. And these op-amps, as I already told you previously, this op-amp is mainly used in different temperatures. So for commercial application, 741 is an op-amp that we know, and C is indicating commercial application. And A indicates the improved version of IC741. And similarly, IC741E, which is a commercial application purpose, and it is an improved version. So likewise, we are observe whenever we are buying any op-amp in a market, we should concentrate on these numbers and the manufacturers. So whenever we are buying any op-amp in a market, we should see the specifications of op-amp which we require. So that means as it is an amplifier, for every amplifier it has input resistance, output resistance, gain, and similarly voltage gain, bandwidth. So these are some of the specifications. Come to this op-amp, it consists of some characteristics. That is input resistance, output resistance, input, there is power supply, and these are common. Not only this, we have to consider the input offset voltage, slew rate, CMRR, and some. We will see further what are these characteristics. We are going to study about these characteristics. So mainly these are some of the op-amp characteristics we should consider while buying or while using in anywhere. We should know these characteristics. These are called as a op-amp characteristics. Right? Along with that, output offset voltage and supply currents, which are also important. Now we'll see, we have studied some list of characteristics. Now we'll study what is these definitions. So input offset voltage. It is the amount of voltage given at the input terminals of op-amp to make the output to be zero. What it means? That means, whenever I'm giving two inputs 0, my output should be 0. But instead of that, I'm getting some value. That is nothing but output offset voltage. When I'm giving two inputs, because we know that op-amp is having two inputs. One is inverting input, another one is non-inverting input. When both the inputs are grounded, output should be 0. But I'm getting some value. That is nothing but output offset voltage. That much of output offset voltage should be compensated at the input. So it is known as the input offset voltage. It is the amount of voltage given at the input terminals of op-amp to make the output to be 0. Ideally, it should be 0. But for IC 741, the value which is equal to 6 millivolts, right? So as we already seen in the pin diagram, input offset voltage, pin number 1 and 5, we are connecting a pot to make the output to be 0. Whenever we are giving input, I'm not getting the output as a 0, then automatically I need to connect a pot between pin number 1 and 5 and make the output to be 0. Next, input offset current. It is the algebraic difference between current flowing at the input terminals of op-amp. It is denoted as I suffix IOS, input offset current, I suffix IOS. As we are saying, it is a differences of non-inverting current and inverting current. So that means IB1 minus IB2. As it may be of positive or it may be of a negative one. Ideally, it should be 0, but for IC741, the value it is equal to 200 nanoamperes. The next character, that is input biasing current. It is the average current seen at the input terminals of op-amp. We know that op-amp is having two input terminals. One is non-inverting, another one is inverting. So the current seen at the non-inverting terminal is named as IB plus, and the current seen at the inverting terminal is known as IB minus. As we are saying in the definition, average, so IB plus IB minus. It is also named in different ways, that is IB1 plus IB2 by 2. For IC741, the value which is ideally should be 0, but practically the value which is equal to 500 nanoamperes. Now we'll see the next definition, difference input resistance. So it is the resistance seen at the input terminals of op-amp. Whenever we are using a multimeter, if you use a multimeter and measure input resistance with respect to ground, then you will observe the value of input resistance is 2 mega ohms. Ideally, it should be of infinity. We know that an op-amp which is having high input impedance, which is a preferable, and low output resistance. So whenever input resistance is more, so that any source can drive that circuit, will not find any loading effect on the source. So that is the need we should have an amplifier which is having high input impedance, means it is a good amplifier. Next, input capacitance. It is the capacitance measured at the input terminals of op-amp, either at the inverting or a non-inverting, either at the inverting or non-inverting terminal, that is known as input capacitance. For IC741, the value which is equal to 1.4 picofarads. 1.4 picofarads. Ideally, it should offer some lesser value. Next, CMRR, common mode rejection ratio. It is the ratio of differential gain to the common mode gain, and always it is expressed in dBs. AD means differential gain. Differential gain means we have two inputs. One is non-inverting, another one is inverting. The difference between two inputs we are observing is known as a VD. And whatever the output it is generated, that is known as a difference output voltage. So that means output difference by input difference is nothing but AD. Similarly, commonly you are giving one input and you are measuring the output. So input common by output common is nothing but output by input, which is known as a gain. So as you are giving common input for the two inputs, so it is known as a common input. And at the same time, you are measuring output with respect to ground, that no output is known as a common output. So common output by common input is known as a common mode gain. That is AC. So depending upon the input and output, and we should express this in dBs. That means 20 log. CMRR is defined as it is a mainly why we are using this. This is commonly entering noise is nullified. So no other amplifier is having this feature, and 741 is why we are preferring, because It is nullifying the commonly entering noise at the input terminals of op-amp. So, which is preferable for our applications. Ideally, it should be infinity for practical IC741, which is approximately equal to 90 dB. Depending upon the type of op-amp. Op-amps are not only available in 741, they are also available in sub 358. So different types of op-amps. But in our subject, we have a 741, which is a commercial application. That means we can use that IC in laboratory environment. Next, output voltage swing. So this is based on the supply voltage. For example, I'm giving the supply voltage both equal plus VCC and minus VCC as a 12. Then output voltage swing is 1 voltage less than, that means saturation voltage. The maximum output voltage that an op-amp can produce is nothing but output voltage swing, which is approximately equal to plus Vsat or a minus Vsat. This saturation voltage is approximately 1 voltage less than VCC. That means if I am giving 12 volts, then I will get plus or minus 11 volts as my saturation voltage. That is only the maximum output voltage swing for that particular op-amp. Next, output resistance. So output resistance is the resistance measured at the output terminals of op-amp. For IC741, it is a 75 ohms. Ideally, it should be 0. We already discussed that an op-amp which is having or an amplifier which is having high input resistance, low output resistance is a good amplifier, because we are not observing any loading effect on source, and that circuit can drive any other circuit you connected to. That means loading effect problem can be avoided. That is based on the resistance. Offset voltage, as we have already seen, pin number 1, previously we have seen that. So in the IC diagram of op-amp, that is IC741, internally it consists of a pin diagram. Observe this, pin number 1, which is a offset null, and 1 and 5. It is not null, so we are using that for the offset null purpose. So if you observe the diagram, pin diagram, offset null, pin number 1 and 5. So offset null. Whenever I am giving inputs, output should be 0. Instead of that, I am getting some value that can be compensated by connecting a potentiometer between 1 and 5. So that is nothing but offset adjustment, where we are using in op-amps. The next definition, that is input voltage range. That is also depends on the op-amp specifications only. So for example, supply voltage plus or minus supply voltage, then the input voltage range is between plus or minus 13 volts. That will depends, as we already seen that op-amps can work up to the supply voltage plus or minus 22 volts, plus or minus 12 to plus or minus 22 volts. So depending upon that, we can adjust the input of input voltage range. Next one is power supply rejection ratio. So it is the ratio of change in input offset voltage caused due to the change in power supply by keeping other power suppliers constant. It's a very, very important definition. Input offset voltage. One time you keep 11 volts, another time you keep 13 volts. And whatever the input, initially compensate that with 0. One time you increase the power supply, another time you decrease. Whatever the difference you are observing in the as an input offset voltage, that is nothing but delta PIS. So the definition is, it is the ratio of change in input offset voltage caused due to the change in power supply by keeping other power suppliers constant. So what is the formula? PSRR is equal to change in input offset, that is VIOS, by delta VCC. What is the other power supply? That is V. Similarly, change in input offset voltage caused due to the change in power supply, that is delta V, by keeping other constant, that is VCC as a constant. So the value for IC741, that is approximately equal to 30 microvolts per second. Power consumption. Every time we have to consider any device, any electronic device is consumed power. For IC741, the power consumed by the IC741, it is equal to 85 milliwatts. Slew rate. It is the maximum rate of change of output voltage with respect to change. It is the maximum how fast an op amp is respond. For example, I'm taking a square wave. A square wave is a series of positive step and a negative step, which is a sudden rise and a sudden fall. So as a op amp internally consists of a capacitor, so we know that capacitor can't change immediately. So it takes time. So how fast the output changes for a sudden rise and sudden fall? There is nothing but slew rate. It is the maximum rate of change of output voltage with respect to the time, right? So that is about the slew rate. So we can define, as already told you, because of the internal capacitance, we are observing this slew rate. That is, as transistors internally, op amps, again, they are designed by using differential amplifier. Differential amplifier is designed by using transistors. So transistor consists of input capacitors. So the maximum current charged by the capacitor to the capacitor value. So for IC741, this slew rate is equal to 0.5 volts per microseconds, because internal capacitance is 30 picofarad and current charged by this maximum current charged by the internal transistors is 15 microamperes, because these are the parameters which are already designed, right? So we are defining this slew rate, as we are saying, by applying not only for sine wave, square wave, which is a sudden rise and sudden fall, we should also observe the response of an op amp by applying an input signal. An input signal, which is a sine wave. So I'm taking input signal as a Vm sine omega t. Vm sine omega t. From that definition, as it is a voltage follower, sir, maximum V naught Vm sine omega t. We are using a voltage follower, and the derivation of that Vm omega cos omega t. So from that definition, we will derive an equation, the maximum frequency where an op amp can withstand without any distortion, that is known as a FM, is equal to slew rate by 2 pi Vm. So what is the slew rate? Slew rate is the maximum rate of change of output voltage with respect to the time. This will indicate how fast an op amp responds for the input. Next, another important definition, that is gain bandwidth product. So for this also, we are using op amp in voltage follower mode. That means unity gain. That means whenever gain is unity, means output voltage by input voltage is equal to 1. That means output is same as your input. So if you slowly change the frequency, it is maintaining the same input and output same. After certain frequency, in terms of some mega ohms, the gain is decreasing. The gain is decreasing. So correspondingly, the gain is decreasing. So we are calculating the output voltage, and we'll measure the bandwidth related to total. So when the gain is decreases, then it is not, so that will indicate the bandwidth. For IC741, the bandwidth approximately equal to 1 megahertz. Okay. So up to this point, we have seen similar output offset. As I already told you, whenever your both inputs are 0, output should be 0. But instead of that, we are getting some value. So that is known as the output offset voltage. So these are some of the characteristics of an op amp which we are considered while purchasing any ICs in the market. So up to this point, we have seen the different characteristics of op-amp. Now we are applying based on AC. If I am giving AC signal, it is an AC character. If I am applying DC signal and observing the characteristics of that op-amp is known as the DC characteristics. So these are the some of the AC applications, AC characteristics where we are using this in AC applications, and we should consider these parameters for AC applications. Similarly, for DC applications, we should consider input resistance, output resistance, open loop voltage gain. So whenever we are applying input signal as a DC, these parameters to be considered. So for an ideal op-amp, we are talking about ideal. So in a world, nothing is ideal, but we should consider while designing, while manufacturing, they consider that ideal op-amp. For an ideal op-amp, input terminals of op-amp, input terminals means non-inverting and inverting. Input terminals does not draw any current, and input impedance is more. So that whenever input impedance is more, any source can drive that circuit. There is no loading effect. And similarly, we are considering that for an ideal op-amp, the gain is infinity. That means we know that voltage gain formula means output voltage by input voltage. So up to this point, we will consider the gain output voltage by input voltage. So as we are saying, infinity means input voltage must be equal to 0 because it is in the denominator. So correspondingly, Vd is equal to V1 minus V2. That means whatever the voltage at non-inverting, the same voltage should be present at the inverting terminal. So these are some of the output ideal characteristics of an op-amp. And output voltage is independent of the current drawn at the output terminals. Thus, the output impedance is 0. Hence, it can drive infinite number of circuits, other circuits. Whenever you are connecting at the output of an op-amp, it can drive that circuit without any loading effect on the op-amp. So up to this point, we are seeing some characteristics, that is AC characteristics as well as the DC characteristics. So these are some of the important definition we should consider for an op-amp. Thank you.